Good evening, everyone. Welcome back to the Algebraic Graph Theory seminar. My name is Thomas Jungspier. I am the chair today. And the speaker is John Bamberg from the University of Western Australia. And today he's going to talk about Ramsey numbers and configurations of finite polar spaces. So, anyway.
Thanks very much. I've only been in the Zoom session for a couple of seconds, but I see some familiar faces. So yeah, hi everyone. So this is the second of a series of the same talk in the same week. So I gave this talk at UWA, but also Anurag Bishnoi is giving a similar talk. It was unbeknownst to me actually when I put the title and abstract in, but we're giving very similar talks. This is in the CMSA series tomorrow. In the afternoon Australian time, so it'll be your morning or something. Okay, so it's about a connection between two different subjects, and it's joint work with Anurag Bishnoi and Ferdinand Ihringer, and it has a little bit of finite geometry at the beginning and a little bit of enumerative combinatorics Ramsey theory towards the end. So polar spaces is the finite geometric thing that I want to first introduce. I'm not going to go through the details. I'll just give you a gist of what they are. So they are geometries, finite geometries. I'll be talking about finite geometries of points, lines, planes, and so on. So an incidence between them. They're associated to the classical groups, the finite simple groups of classical type. So things like symplectic groups, orthogonal groups, unitary groups, and these are the natural geometries for those. So they act on a vector space, and then you have some sort of form on that vector space, bilinear form or a Hermitian form or a quadratic form. And you're taking the subspaces that are zero under that form, or the form restricted to that subspace is zero. So we care about things like singular subspaces for a form, or in other words, totally isotropic, or if you've heard those terms before. And these are zero under the form, if you like. So just think of it as you're taking out some subspaces of a vector space. And one nice way to think of it is if I think of the lattice of subspaces, that's not a very good circle. Let's try another one. So the lattice of subspaces of a vector space, then you think of at the top, you've got the vector space, down the bottom, you've got the zero subspace. You might have one-dimensional subspaces down here, two-dimensional and so forth. And you've got an incidence geometry, a projective geometry actually from this subspace lattice. And the singular ones, I'll find a different color for those. These ones might be singular. Most of these will be singular down the bottom here, quite a lot of them. And then it starts to rarefy as you go up. And that's because being a singular subspace is a property that goes down. So if you're contained in a singular subspace, then you're singular. So it should become rarer as you get higher. And it stops about roughly halfway in the vector space. And they all have a common dimension at the top here. And so you're taking out some subspaces and you get essentially a meet semi-lattice. So the intersection of two singular subspaces is singular. Oh, this is for a non-degenerate polar space, for those people who are wondering. And the things at the top here, the old-fashioned term for these is generators, because in some sense they generate the whole polar space because it's closed under going down. And so the maximal ones here, I'll call them generators. And then underneath you have singular points, singular lines, and so forth. And you have an incidence geometry. And this is a very natural geometry in the sense that there's a wonderful theorem by Buchenhout and Schult in the early 70s that it's characterized by this type of geometry is more or less characterized, I won't go into the fine details, with the following axiom that if you have a point and a line in this geometry, so one of these blue points, then you either have two cases actually, so I should draw this picture twice, two cases, that this point is collinear with just one point on this line. So that means there's a line through that point which meets the other line in a point, and that's the only singular subspace here on this line that is on a line with this one, or all of these points here are collinear with the point. Okay, so I'm thinking of a finite polar space here. So look at this and you get collinearity all the way through. And this is how you actually get higher dimensional subspaces, by taking these types of objects. You know, this would span a plane, for instance. And so this is sometimes called the one or all axiom. And it's also got to be a sensible incidence geometry, so 2 points run at most one line and things like that, but that all sort of follows from this axiom. So this is a nice synthetic characterization of this algebraic looking object over here. And that's more or less, if you combine it also with the theorem of Feldkamp and Tits, you essentially, these are the only polar spaces, except for when you only have points and lines and no other singular subspaces. Then there are other constructions of polar spaces that don't arise from vector spaces. But for the purposes of this talk, think of them as all coming from a vector space equipped with a form. Okay? And polar spaces seem to turn up a lot. They are used in the construction of nice graphs, nice association schemes, strongly regular graphs, two-weight codes, Turan graphs, all sorts of things. And you'll see today that they might give rise to some things in Ramsey theory. Now, some recent uses of where polar spaces have cropped up in extremal combinatorics. Collin and Ferber, they didn't explicitly say this, but their construction of graphs which achieve a better lower bound on multicolor Ramsey numbers is essentially using symplectic spaces over the field of order 2. And then Mateus and Vestrada's recent result is using emission spaces of rank 1. But I guess even though these are, to a finite geometer, fairly trivial polar spaces, the geometric intuition was something that helped in each of these instances. I guess particularly in the second case, it's some sort of geometric experience, I suppose, in finite geometry was useful in each of these breakthroughs. So basically we have, in these two cases, but there's a few more other ones which I haven't mentioned, there's finite geometry here and Ramsey theory here. And there's been a lot of attention on trying to go this way, but nothing so far about going this way. Okay, so that's what we observed, that we could actually probably go the other way and say something about objects in finite geometry from things we know in Ramsey theory. Okay, to start off with, to get somewhere with configurations in finite geometry, I need to introduce another thing, and it's got quite an ugly title. So they're partial M ovoids. I didn't come up with that. That's a little bit of an unfortunate thing that there's a parameter in the title of M, but it's quite a simple thing. It's a set of points of a finite polar space such that every generator, so think of maybe a plane or something like that, would intersect this set in at most M points. In fact, if every generator does, then every singular subspace does. Okay, so we have this nice intersection property, and it's called a partial M ovoid because of that less than or equal to, because if you have equal to M, then you get an M ovoid. And they're older, they at least go back to Segre, but they were called M ovoids by Jeff Tuss in the 1980s. And if you do have an M ovoid, so in this other situation, then the size of such an object just comes from a double counting argument. And you end up with the following, and I'll just point out what these parameters mean. So Q is the order of the underlying finite field. R is the rank of the polar space. And what I mean by that is the number of objects you have, or the dimension of the algebraic dimension of the generators. So if you've got just points, lines, and planes, then it's rank 3. And E is a parameter, it's just a small number, which gives you the type of the polar space, so a half or one or something like that, or zero. And partial M ovoids, there's not much known about their size. So they're bounded above by this. But we don't know in the cases where there don't exist M ovoids what the largest size of a partial M ovoid is. Well, we don't know much about it. So I'll say what we do know. Is that in the next slide? Let me just double check. Oh, I should mention that the polar spaces that I'll be talking about, they come in different flavors, and I'm going to lapse into geometric notation. So there'll be Hermitian spaces with 2 different dimensions, maybe, but I won't go over all of these details. There'll be orthogonal spaces, they're called quadrics, and then symplectic is the main one I'm going to talk about. So this W will turn up, and that means symplectic. The reason for that is maybe apocryphal, that Hermann Weyl named it after himself. So yeah, symplectic spaces get a W for some reason. But we do know something about M ovoids. So if an M ovoid exists and you're in half of the polar spaces, if you like, so the symplectic, or I've put the groups here, so I forgot I did that. So this would be the symplectic, the orthogonal minus case, and even dimensional unitary or Hermitian. Then you have a lower bound for M in all of these parameters I was just talking about before. Now, finite geometers love to have these precise polynomials for things. And we're going to turn that on its head a little bit here. So, oh, I should mention the E here is 1 or 3 over 2 or 2. But I want to get away from using this sort of precise formulation of the size of an object, and instead talk about the asymptotic growth of the size of an object. So if we fix Q here, then this bound is something like, if I write it in Landau notation, then it's big omega of Q to the R over 2, roughly Q to the R over 2 minus 1 or so. And so that means that eventually, as the parameters grow, so as R grows, M is a constant factor times Q R over 2, at least, okay? So it's the opposite of big O, if you're not familiar with this notation. And if we instead fix, so let's say Q is a prime power, P to the H. If I instead fix the rank and this little exponent, then it changes what we're interested in. You end up getting big omega of P to the H R plus E minus 1, 3, sorry, 3 over 2. Okay, so let's have a think about this. So if you fix Q, this is exponential as R increases, whereas if we fix R and H and we vary the P, the characteristic, then it's more of a polynomial, okay? So what you're interested in changes. What is a good lower bound is different when you're thinking of it asymptotically. And so in particular, there's a recent result just came out this year by De Boerle, Jonathan Marnhartz, Valentino Smaldore, that they have another bound, which is a much longer sort of polynomial in Q. And if you fix Q, you end up seeing that M there's a better bound, square root R Q to the R over 2. So there's a square root of R in there. But if you do the second case that I was talking about, you don't improve the bound. Okay, so it's the same bound that they get. Anyway, so we know a little bit about M ovoids, but only in half of the polar spaces. Okay, so we don't really have a lower bound on M for other polar spaces. There are other results that I'm not talking about here. There's a beautiful result of Klaus Metsch and oh, what's his name again? I've forgotten. Drawn a blank on the other guy's name, but they have a nice modular congruence on M for this case here. Okay, so what about partial M ovoids? So we have a simple observation. If you take the collinearity graph, so what I mean here is in a finite polar space, take the points to be the vertices. So I'm making a graph and join them by an edge if they are collinear, if they lie on a line. So that's the collinearity graph. But now restrict it to take the induced subgraph on a partial M ovoid. Okay, so partial M ovoid is sum of the points, take all the edges that are induced, then because it's a partial M ovoid, it doesn't have any cliques of size M plus 1. So I've written here that it's got no cliques. That's my little graph theory notation. It's a complete graph on M plus 1. And the null graph here, the complement of the complete graph on T plus 1, it doesn't have co-cliques of size T plus 1 when T is the largest size of a partial 1 ovoid. And that's because if I have a co-clique in this graph, it's a set of points known to a collinear, and that's a partial 1 ovoid. And so it's kind of nice that the cliqueness of the graph is got to do with partial M ovoids, but the co-cliqueness is governed by partial 1 ovoids. And so this looks like Ramsey for those people who know all about Ramsey numbers. So just a little reminder, I'll be using RST for the largest number of vertices of a graph. That has no S-clique. Oh, I should say it a different way, hey? So KS free and no co-clique of size T. Okay, so Ramsey's theorem is that this is actually a finite number. And for instance, you might be familiar with that these numbers are only known in a few isolated cases. R33 is 6 and so forth. And so another way to talk about it is edge colorings, two edge colors into two colors, blue and red, of the complete graph, and you're always getting a monochromatic clique in any two coloring, and that's the same as this definition here. Okay, so when we look at what a partial M ovoid is doing for us, it's giving a lower bound on Ramsey numbers. Okay, and in particular, if we apply very simple things we know about, oh, I should mention one more thing. Why does this work? Why does this work? So if I take a clique, so if I start drawing lines between 4 points here down the bottom, then the subspace that this clique generates, the span of these points, will be singular. Now think of a bilinear form or a sesquilinear form. The fact that you have all of these orthogonal under the form will mean that any linear combination of them will also be orthogonal. Okay, so just have a think about that. That's a little exercise. So the subspace generated by a clique will be singular, therefore it's contained in a generator. And because it's contained in a generator, that's why we have Km plus 1 free, okay? Because every generator meets in at most m points. So yes, it seems very obvious to a finite geometer, but I should spell it out. Now, okay, so clique spans a singular subspace. So we have this nice, we can actually apply Ramsey numbers to partial M ovoids. And what do you get? Well, I've got enough rooms. Maybe I'll delete this picture. If I take the size of a partial M ovoid, then I know it's at most the Ramsey number Rm plus 1, but also we have a trivial, well, a folklore bound on the size of a partial 1 ovoid. N is the dimension of the vector space. And so there's a P rank bound for the partial 1 ovoids, which gives us this. Okay, so I've just slotted that in there. And then this is roughly N plus P to the HM p minus 1 if I use the classical upper bound by Erdős and Szekeres. Okay, so we get a nice bound just using Ramsey in terms of the parameters m, p, h, and n. So it's quite a nice little observation. It's not a particularly good bound, but it shows that there is one. So it's not too bad. It can be, well, we can improve it a little bit. So that's what I've got on the next slide. If you have an M ovoid, then in fact you can get a lower bound roughly on M in terms of R, the rank, and P, the characteristic. Okay, so if you tune it up a little bit, you do a little bit more calculus and things like that to play with the numbers, you get this inequality here. So this is just log to the base P here of 2M, so it doesn't contribute a lot. And in particular, this is a new bound or new existence result on M ovoids, because remember, the other ones were only for the same 3 families of polar spaces. The one that was in 2007, and also the recent result of de Boerle et al. And so, yeah, this would apply to the other polar spaces because those techniques simply cannot be carried across to all polar spaces. So the bound is weaker in general. You know, it's not as good as the ones that we had before, but it works for all polar spaces. Not only this, but we could, this is really due to my other 2 authors. I'm not so good at probabilistic constructions, but probabilistic constructions come into play here. So now that you've got your induced subgraph, you can start playing with the edges and put a coin on them. And you get that for M at least some constant times R, and this constant just has to be at least a half. So you can choose it to be whatever you like, 0.51 would be fine. Then there is a partial M ovoid. Of size Q to the omega R. Okay, so we can make fairly large partial M ovoids in a polar space with rank R. Okay. So this is very strange to a finite geometer. They probably wouldn't like this very much, so because it's a probabilistic construction. Okay, it hasn't really been. I don't know of any like that, and so it really is leaning on the probabilistic construction of Ramsey graphs. For m equals 2, you can do slightly better than this. So we know that we know this Ramsey number, so we know something about these Ramsey numbers, I should say, we just know a bit more about these than in general. And we get an upper bound on the size of partial to ovoid. So we get R squared over log R. So there's all sorts of things you can do here. In particular, you could apply this to small Ramsey numbers. If you're familiar with this table that's in the dynamic survey, I have tried to do that, and I only managed to get a partial M ovoid which was close, like was 1 integer away from one of the bounds, one of the lower bounds. So I haven't been successful in improving the Ramsey numbers in the table yet. So that's something to be done. I'm going to show another connection now. M nearly orthogonal sets. So this goes back to a question of Paul Erdős, of course, in 1988. And then there were some breakthroughs by Alon and Szegedi in the 1990s, which made the area popular. So it's another area of combinatorics. And every time we saw a paper come out on nearly orthogonal sets, we were always curious. Like we were thinking surely finite geometry can do something because they are simply just the same as an object in finite geometry. So I'll start off with Oddtown. So you might be familiar with this, but it's basically if you take a set with T elements and you take a family of subsets of this. Okay, so you've got just a lot of subsets with the following condition, that the subsets have odd cardinality, and any two intersect an even number. So it could be empty, for instance. And it was asked what the largest size would be. This is an old problem, another one of Paul Erdős, and it was answered by Bellekamp in 1969. So most of you will probably know this because it's a nice application of linear algebra, and you see that the size of f is at most t. So you take the usual argument is, think of these sets as, well, take their characteristic vectors and then look inside of a finite vector space over the field with two elements, apply the dot product, and you see that such a set would yield a linearly independent set of the vector space, and so you get at most t. So this is very different to if I change this condition to even, you get exponentially many, you get 2 to the power t over 2 elements. Okay, so this is a nice little counterintuitive combinatorial property that you can put in front of your linear algebra class. And there's a little generalization of this. So instead of this second property here, that intersection is always even, I'm going to just change this. So I'm going to say that there are subsets for all subsets. So for all distinct S1, S2, if I take m plus 1 of them, then there is some pair such that they have even intersection. Okay, so when m equals 1, this is an odd town family. Oh yeah, I forgot to mention it's called odd town because it's this set is citizens in a town, and these sets are clubs, and you're trying to put people into clubs. But this here is a generalization of that, where we say that for every m plus 1 of these subsets, there is some pair that intersects an even number. And if you take the characteristic vectors of these, you just get exactly what a m nearly orthogonal set is. So m nearly orthogonal would just be vectors v1 up to vn, let's say, in a vector space. And in the case that this field is the field of order 2, these things correspond. But in general, we can take any vector space, finite vector space, and have these conditions that any vector here in this set is not orthogonal to itself, and for any subset of size m plus 1, so we have the similar quantifiers as above, but we would have, instead of intersection even, we would have dot product 0, so orthogonal. So that's why they're called nearly orthogonal sets. Okay, so there exists an I and j, which is equal to 0. Okay, so this odd town, this generalized odd town, is an m nearly orthogonal set over the field of order 2. Okay, and there's a little trick here. Let me just check what's in the next slide. Yeah, whoops, I'll do it here. So there's a little trick that if I take this set of vectors, and now my field is F2, I could just add the all ones vector to each one, and that would change their properties. In particular, I want D to be odd. So we'll flip these values here. And instead, we will take the vector space to be the even weight vectors in an odd dimensional vector space. And the dot product would give you an alternating form on this, on V. Okay. And so to keep a long story short, you can massage these sets of vectors so they give you exactly a partial M-ovoid of a symplectic space over the field of order 2. Okay, so these things are equivalent in the case that you have the field of order 2. So you get, in blue over there, the partial M-ovoid of a symplectic space. Okay, so it was kind of, while we were working on this, all these papers started coming out on M nearly orthogonal sets and embedding them in vector spaces and all this sort of thing. And we were struggling to keep up with it, and all these results kept on coming out, and we kept on using them. They kept on being just the right results at the right time. So there's quite a lot of luck in this project, and I'll show you what I mean. So for example, this paper came out in 2022, Golovnev and Haviv, that using, so I'm paraphrasing what their result is, because they don't know what a partial 2-ovoid is. They had M nearly orthogonal sets. And they show that there is a partial 2-ovoid of this symplectic space of the field of order 2 of this size. Okay, so it's just a bit more than linear. Okay, so it's exponential. And at the same time, we had constructed a family that was linear, and we wrote a conjecture down that it was linear. It was totally wrong. But for small values, I think for t up to 13 or something, it fits the maximum number fits a linear function. It's something like, I've forgotten what it was, 8t minus 11 or something like that. So that was just a vagary of small numbers. And so, but it turns out to be not linear. So that was quite a funny thing. And then we discovered that there was a preprint that came out at the time we were looking at this, which has an even more general result. So there's a constant delta, so that for every partial M-ovoid, you can get, for every M, sorry, you can construct a partial M-ovoid of this size, M over log M as the exponent. So it's very different to what we had initially thought. We knew that maybe if M was large, that they would start growing, but we weren't sure what would happen for small m. Oh, I should mention here as well that the odd-town result is kind of saying what happens to a partial 1-ovoid. We know what that size is. Yeah, I should keep to this notation. In fact, it reaches this size. A partial 1-ovoid has size at most 2r plus 1. This is an old result in finite geometry, essentially, but that's, you can think of that as the odd-town theorem. And also, we know from what I said way back at the beginning that a partial M-ovoid of the same space has size at most, and this is m to the 2r plus 1. So that gives us some validation. We weren't that crazy. We were actually thinking that at small values, it would grow linearly, right? So because we had that for partial 1-ovoids. We weren't sure what was happening for partial 2-ovoids. That was what we were interested in. Anyway, I'll show you our other results, and it's a very strange construction. Let's check on the time there. Okay, so here's our result that there is a partial 2-ovoid of this symplectic space, now with a different exponent. Okay, so it's bigger than what we had before. So this is the exponent here. A couple of years ago, 1.0889. We've gone a little bit bigger. And the way that's done is might seem very strange. So I want to go through that. So, so where does this number come from? This is, you'll see it in a moment. It's actually log 4 over log 2 plus square root 2, to be precise. Anyway, so we actually use quite a lot of interesting graphs here. So this might be of interest to others in the audience who in graph theory. So you take a Cayley graph Oh, this is a different gamma, sorry about that. Where we think of using f2 to the h direct product with itself, thinking of it as an abelian group, and you take this joining set, AA cubed, where your A is non-zero. This is a famous graph. And it was the one that Noga Alon used to give a constructive lower bound for Ramsey 3T. So Alon used this graph, it's triangle free. And he showed that R3T was greater than T to the 4 over 3. Okay. All right, so what you do with this is you take a triangle-free graph, such as this one, and what you want is to have low complementary 2 rank. So let me explain what I mean by that. So I'll write this, rank subscript 2. I'll take the adjacency matrix of the graph. I'm just going to add the identity matrix to it. Now, for the experts in the audience, you'll realize that this is pretty close to being the complement, the matrix for the complement graph when you think of it over the field of order 2. But this is also a bound on the co-clique number. So if you take rank subscript 2, what I mean here is you take the rank when you think of this matrix, which only has small numbers in it, you think of it as being a matrix over the field of order 2, and then you take its rank. So that's what 2 rank is. And you want this to be small. So let's say that this is n to the 1 minus delta or something like that. So I'll use those parameters in a moment, where your delta is a fraction. And we want a triangle-free graph on n vertices. Okay. So we're thinking of the 2 rank as some logarithm of the number of vertices. And then there's a beautiful theorem that we didn't know about, which is due to Lempel in 1975, which is that if you have an n by n symmetric matrix, over the field of order 2, with at least one non-zero diagonal entry, and it should have rank R, then there is an n by R matrix B over F2, such that, this is the amazing thing, and it's a Gram matrix so you get M equals B transpose. Okay, so that's to me, that was quite a surprising result. Normally, you're accustomed to doing this with positive semi-definite matrices. You like to use this trick. But here, we'll have something that might be very far away from being positive semi-definite in any sort of shape or form. You're over the field of order 2. And you still have this property. So I'd like to know from anybody who's watching today if this extends this result to other fields. I don't know. I haven't found anything. Now, what you do is you write this matrix that we had above as B transpose, because you can, due to this theorem. And then your B, you take the rows of B, remember it has rank R, it's an n by R matrix. And so you get an embedding of your graph, essentially, via this correspondence to inside of a vector space of dimension, well, I should say the rank of this complementary 2 rank. So if A plus I had rank T, then you get, in fact, this gives rise to a 2 nearly orthogonal set. inside f2 to the t. And your n is t to the 1 over 1 minus delta. So there's quite a lot to work out. But basically what you want are triangle-free graphs with low complementary 2 rank, this number here. And it was funny because Anurag said, well, I want to use this graph because Alon's graph is a little bit of a gemstone. It's got to be something important here. And it came up, I'll see if it's on the next slide. No, not quite yet. I'll put it here. It turned out that a paper came on the archive just as we were thinking about it by Deng, Wang, and Zhang, all in SUSTech, okay? And it was early 2024, that they looked specifically at Alon's graph and worked out the complementary 2 rank for completely other reasons, not for anything to do with our project. And they ended up with this bound. So that's where this funny number comes from, the 2 plus square root 2. And that's for all h. And so what you do then is you can bootstrap this example. You take this graph, you take its strong product, and you end it keeps the complementary 2 rank low and keeps it triangle free. So you can get an infinite family of graphs this way. And so that's our next result, that we can actually take a different graph. In fact, we improved this result. For every epsilon, there is an m, so that we can make an infinite family of km-free graphs with complementary 2 rank t, so you can get arbitrarily close to this number here. Log 16 over log 10 is the exponent. And this number here, this exponent is 1.20412. So it's not so good for small m, this little construction, only in the specific case we had before. So we were using this graph, and it has 32 vertices, this Cayley graph here. There are 9 elements. These are the standard basis vectors. So I've taken E1 up to E5, and I've added them in certain ways. And it's actually a cap of a projective space. So that's why we get a triangle-free graph. So it's a linear representation of a cap, if you know what that is. And this was the champion example. So I was just going through lots of Cayley graphs, going through graphs of homogeneous configurations. In fact, I was going through a database and looking for low complementary 2 rank. And it's actually not very common. So if you're interested computationally, you go through these graphs, you just print out when you get, most of the time you get full rank. You get full 2 rank. And then every now and then it dips. And so I was looking for the best ones, and this one popped out. And this is all connected to rank Ramsey because, so this rank Ramsey is a recent thing. It's similar to Ramsey, got this little subscript K. It's the largest n, such that a graph of order n is KS free and has rank, so this means rank over the real numbers, of A plus I is at most T, because this is still a bound on the Köklig number. So this is a generalization. This is at least the size of a Ramsey number. And using the same graphs, we found that they were good for this problem too. So there were kind of these offshoots to our problem, these nice little corollaries that we could actually get a nice bound on rank Ramsey. So this is roughly, in other words, if you write this, I might get this wrong, but if you write this another way, this is, let me get this right. So 32 over 11, if that's right, plus little o of 1. Have I got that right? Something like that. Okay, so if we write in this form, the previous best example was, what was it? So using the Alon graph, you got something like, let me think for a moment. Yeah, you got using, no, their results, sorry, the results of Haviv and so forth, they got something like 10 over 8 or something. It wasn't as great as this bound. And then you can also just apply it to random numbers, which is what Ferdinand did. And he's found some nice curious thing is that for t sufficiently large, let me see if I've got that on the next page, and I'll put it here. To t sufficiently large, all of these things imply that there is a partial 28 ovoid. Just to test this out, where the size is 1.2936. So you're looking for local minima when you're playing around with these numbers. And also 42, you wanted to see what happened for 42, and you get t to the 1.15 and so on. So it sort of shows that you can, it gets better as when m is smaller. So this graph that I had before, this one here, I forgot to mention, yeah, it's a triangle free, but it has, so it's got order 32, but its complementary 2 rank is 10. So it's 32 versus 10. And so this 11 actually comes from the dimension of the eigenspace, which has eigenvalue 1. And so that's why we get 11 instead of 10. It's like 1 more than 10. Okay, but I just wanted to report just at the end here on, there's a better example, which has just recently been found. A student of Anurag Bishnoi, Ananth Ravi, has a graph that has order 64, Cayley graph, and its complementary 2 rank is 18. So you can improve this result, and you get a different exponent. So I had 11 over 32. So I think you can get 17, roughly 17 over 64 here. No, 64 over 17. Oh, yeah, that's it. 17 over 64. And in fact, I think he's been able to extend this to an infinite family, which makes it quite interesting. It's going to show that it converges to a number. I think it's 1 1/4 from memory. So yeah, there's more to do there, but it's beautiful connections. Finally, just to finish off, this is a nice connection between some Ramsey problems and finite geometry, but also it's really a very strange construction. Remember that we had this triangle-free graph, and we put it through this funny correspondence. We embed it in a symplectic space, and it's a very unusual construction, and we're getting sizes which are very not finite geometry. We're getting the asymptotic results, and that's perhaps what the truth is. So it's kind of changed how we think about some of these objects in finite geometry. Thanks very much.
Okay, thank you very much, John. Are there any questions?
I am. Hello, John.
Hi,
Can you hear
Thomas.
me? Yeah.
Yep.
Congrats on that. It's really nice. When you're talking about the add-ons graph, I think immediately, and I'm sure Anurag thought about that, looking at the extreme, like the Ramsey graph, which is the triangle-free, like a random triangle-free graph. Do you have any hope of computing the 2 rank for that kind of stuff?
Oh,
and what could give you, like if you're looking for triangle-free graph, the best ones are going to be probabilistic.
Yeah, that's right. Yeah, that's a good question. That's, I think, what some of the other authors are looking at, actually. These are Haviv, and also, I didn't mention, actually, Benyamini et al. What was the other authors? That was what I think they were interested in. Okay, so what it would be for a random graph. And so they do have bounds. So if I could find the reference to their paper. Oh no, I can't find it right now, but it's in the references to our preprint, which is on the archive.
Yeah.
And yeah, there it is, Benyamini, Lineal, and Schreibman. So our rank Ramsey, I totally forgot to mention this. Yeah, this is an improvement of their result. So they were interested in that problem. Lineal and Schreibman. Yeah, so I think that's currently going on.
Yeah, if you show the add-ons graph, you have to go all the way.
Yeah,
I guess.
yeah, exactly. Yeah.
Okay. And while I'm here, these rank Ramsey parameters, do you have bounds to compare with traditional Ramsey numbers? Like, does it exist like some relations between them, or?
Yeah, kind of. I think they're attempting to show that it's much different to the Ramsey number bounds. So I don't remember it offhand, but they give a general bound in the Benjamini result and the Benjamini paper, which is asymptotically very different. You know, it's not like 4 to the t minus 1, that sort of thing. Yeah. But I think I didn't know that until that paper. So their earlier work, I think even a couple of years ago, maybe it was conjectured that they would be running a similar asymptotic bound, but it turns out it's not.
Okay. I don't know. I have zero intuition here. Okay. Well, thanks.
No worries.
I have a question. Initially, you conjectured that the size was linear, and then we saw that it can be with an irrational exponent. Do you have a new conjecture about the growth?
No, not really.
Not
We're a
really.
bit scared of the conjecture now. Yeah. Yeah, I don't know. And I don't even know how it would change with M. We had this M over log M, which is probably what happens actually. It's probably M over log M. But yeah, I don't know. It's very tricky. Yeah. And it's very hard to see by computer because you're fixing the field and changing the dimension. Very unlike what you do in finite geometry.
Okay.
In that conjecture, the M over log N, there's a constant in front. Do you know what's a constant? Like, is it like extremely small, or is it something?
Yeah, you can work out, in each case, you can work out the constant. It just takes it takes Ferdinand a lot of time. So we kept on asking him to do it. Yeah, you can do it. So you can go back through all those papers and you can find the constant. Yes, this delta comes from the other work of the other authors using the strong product and everything. So, but yes, you can work out that constant.
Okay, thanks.
Okay, thank you.